When I gave this talk before, it was about 40 minutes, and so I'll try and get it all into 30 minutes. So I'm Robert Stewart, and I'm the Chief Architect at Castlight. And so what I'm going to talk about today is how Castlight Health uses MongoDB to do geospatial searches for healthcare pricing data. So what I'm going to do at first is just give a little bit of background about Castlight Health to give some context for the particular problems that we needed to solve. And then I'll go a little more in depth into those actual problems from the business perspective, as well as kind of the technical problems I had to solve. And then, as is often the case, you have iterative solutions to this. You take a shot at it and do something simple, it works great, and then things change. The data grows dramatically, and then you have to adjust to that and scale up your solution. And so we went through a couple iterations of that, and I'll talk mostly about the final solution we came up with MongoDB and geospatial indexes, and even there, kind of like we iterated on which indexes to use, and then running the database on top of SSDs and why we did that and why there's huge value in doing that for our use case. And finally, I'll talk about an operational aspect of what we did, taking advantage of a feature in MongoDB called replica set that made it very, very simple to flip between big bulk sets of data with really no impact on our production system. And this is, it's nothing earth-shattering, it's not patentable one-click flipping or anything like that, but for just a little bit of extra cost around the SSDs, it gave us incredible operational flexibility. So if you can do it, I definitely recommend it. So Castlight we're a growing startup, so we're probably at about 270 people or so now. We're in San Francisco. And so we've been there about 5 years, and what we do is we develop hosted and web applications that provide consumers with unbiased information on healthcare cost and quality. And so you can effectively shop for healthcare based on cost, quality, and convenience. So we sell to employers, though, so employers and health plans. And so typically we're selling to medium to large to mega large employers who usually they're self-insured, which basically means that rather than the insurance company taking the risk, they're taking the risk, but at reduced premiums. And so they have a lot of skin in the game around how much is spent on healthcare and how healthy their employees are. And of course the consumers do, because a lot of these companies are switching to high deductible healthcare plans. And so the employees and their adult dependents that we support, it's very important for them to be able to search for high-quality, low-cost healthcare providers. So we've taken in about $181 million in funding. Fortunately, we still have most of that. And things are going pretty well, so we've gotten some pretty good recognition in the area of what we're doing, and growing fast, selling huge customers, which of course has caused my database to grow enormously. And we're hiring, as always. So if you're an employee of a customer of Castlight, this is what you would see when you log into our application. And we have a web application, a mobile web application, and then native mobile applications on iOS, Android, and Windows Phone. And so this is the main web application. So an employee or one of their adult dependents could get access to this. So in addition to being able to see information about your past care, so we have nice charts and graphs so you can see how you and your family are using healthcare and what things cost, which providers you're going to. And you can see information about your plan, but you can see real-time information. So we get real-time information about where you are in your deductible, and it can be very complicated. There can be individual deductible and family deductible and these things called sandwich deductibles, and then the co-insurance and the copay, and there are a lot of complicated provisions. And so rather than you having to kind of run those numbers in your head of how is this going to affect the cost if I go to a provider, obviously we have the computer do it because it's fast and it's accurate and it doesn't mind doing those things. And so what we do is we provide the user with personalized out-of-pocket estimates for a particular procedure or service before they actually go to that doctor. And we can show you comparisons. And we have a lot of quality data that we'll show. So out in the middle of this, you'll see, this is where you would search. And so the big red search button out in the middle. So above that, there's a zip code that is there right now, but you could make that a street address or city and state. And we will geocode that to a latitude and longitude. And we just use Google to geocode that. And so that'll be the search origin. The latitude, longitude will search around. And it defaults to 25 miles, but you can make it 2 to 100 miles, the search radius of where you're going to look. And we're going to find all of the providers that perform that particular procedure or service that are in network for you, and we're going to show as much as we can estimates of your out-of-pocket cost. And so very specific to you. If somebody else logs in, they're somewhere else in their deductible coinsurance, they'll see different price estimates. So let's say you searched on primary care for adults. And so the pretty common thing, you're looking for a primary care physician. And so we'll kind of work left to right in this. So like on the left side, you see you can adjust the search radius. And then there are a lot of filters. The initial visit is typically a little bit longer, and so the cost is based on time for these office visits. And so we need to know, to give you an accurate estimate, a little bit about the visit. And then there are a lot of filters. So we'll limit it. We'll show you, how many male and female and various specialties like internal medicine. And we'll show you the actual numbers for those. So it gives you a sense of like, if I were to filter against these things, how much is that going to reduce the result set before you actually do it? And they'll change as you click on them. And then at the top in the center, you can see we show the price range. So we've gotten the min and the max prices for all of these providers for which we can provide estimates. And so we have to go get all of this data. So in some cases, like you search for adult primary care in a major metropolitan area, and this is like in downtown San Francisco, you might actually get thousands of results back. So it's a lot of data we have to pull back and do all these out-of-pocket estimates on, and within this location. So definitely, you can imagine where geospatial indexes become very important for this to perform well. And so then on each of these individual providers, if you click on those, we'll show you quality information about the providers, as well as the cost of other procedures. Maybe you see a great price on some procedure and like, I think I'll go there and get that. But it gives you a sense of the overall cost of that particular provider for other procedures. So, so the two main things we needed to do is that kind of search that I just showed. So we're looking for the prices for a particular procedure or service performed by any of the providers that are in network for you in a constrained geographical area. And so that's the main thing I'll talk about today. Also, there's the lookup for all the prices for a particular procedure by that single provider. For all procedures by that single provider. But that's obviously a very simple thing to do. You can do that with basically any kind of database. You could index that. And also, we want sub-second response. We want this to be super snappy. We don't want this. We want this to be like any kind of consumer shopping sort of website. And so we demand of ourselves that we keep the search time under 1 second for these searches, even when we're returning thousands of prices and doing all these calculations to give out-of-pocket estimates. So as I mentioned, obviously you need a very fast geospatial index to pull that off. And our rate count and this is the actual, this is the curve of the rates that we have in our database right now. And on the far right, in August, we hit 1 billion rates that we have. And again, a rate is a procedure performed by a provider at a particular location as part of an insurance network, because the price may be different. If you go to the doctor at his clinic or go at a hospital where he has privileges or she has privileges, the price can vary, and we have that information. And the way we do this is we take in medical claims. So we pull in, right now we have over 1 billion medical claims that are de-identified. And we have a team called the Revenge Team, and they do reverse engineering. And so they take in these medical claims and they reverse engineer the negotiated rates between the insurance companies and the medical providers. And we have a Greenplum cluster that we use for that. And so from that, we've generated 1 billion of these rate estimates for healthcare pricing all over the US. And every month, these increase. So we do another one of these runs, we get more claims to analyze. And just in going from July to August, we went from 750 million rates to 1 billion rates. And so obviously a pretty big jump that we needed to be able to handle and get that data into the app with minimal impact, ideally no impact on the actual users. Another thing about it is that it's difficult to index the data so that you always get sequential reads. So with databases, typically you're using a most common type of index is a B tree, and really specifically a B plus tree. And that kind of goes back to the nature of block devices and sequential versus random. So typically, there are a lot of reasons to create an index on a table or a collection of documents. And two of the main things you're trying to do, one is you're trying to reduce the data, the items that are in the collection or table to as small as possible, as close as possible to the result set before you return it. And the other thing you're trying to do is try and make sure that those items that you do look at have locality on the physical device you're storing it at. Now that's really important on a hard drive because while the sequential read time is really fast, basically the bandwidth of the drive, the random read time is affected by the seek time on the disk. So now you're looking at like maybe 10 milliseconds or so seek time. You do a lot of random reads and it really adds up. But as it turns out, with SSDs, it totally changes the story because with an SSD, the random read speed is much, much closer to the sequential read speed. And so you don't have to worry as much about this data locality. There's not a big penalty of doing more random reads. And the payoffs of that is you don't have to worry as much about the index. You don't have to have, like in my case, I would have had a very complex, big index, takes a long time to build, a long time to maintain. The big thing is bad, of course, on an SSD because it costs more, but also just the time of maintaining it as well. So it's kind of, you can cheat on that of having a simpler index if it's on an SSD. And the cost has gone way, way down, so definitely worth looking into. So no, our system, there's lots more moving pieces in it, but just as far as like the pricing retrieval aspect of it, this is what it looks like. So up at the top, the user, they're coming in through a web browser, or they've got a mobile web browser, we have a mobile app, and then a mobile web app, and then these 3 native mobile apps. But all those, however they come in, it all funnels down through. It's like there's a Ruby on Rails app, and then we've got client-side apps that are single-page apps written in JavaScript with Angular. But it eventually comes down into our service layer, and that's written in Java. And so the pricing service is kind of the layer that interfaces down to the prices. And so one nice thing is, I'll talk about what I started with was MySQL. I was able to transition it to MongoDB just in that layer and not affect anything above it. So what we started is, and this is back when we had maybe 2 million rates, that were these 2 million prices that we're looking at, it just store it in MySQL, pull it out of MySQL when the pricing service starts up. But once that hit about 150 million rates, it started to become problematic because what we need to do is, because there's no geospatial index built into MySQL, so I had to do that in Java and the pricing service. So I had to build at least the basic part of that index. And so that takes time to build. And so I eventually was hitting, like I had a 55 gigabyte JVM heap, which is rather large. And I was spending a lot of time on GC tuning. CMS collector, that is your friend when you're doing things like this. Way, way better than the parallel throughput collector. So it's a lot of time that I'm like trying to work around this. And then it was taking 20 minutes for the pricing service to start up because I didn't want to slam the database while I was reading in all that data. And then I still wanted to background cache all the additional data, and that was like 3 hours before that happened. So when I would start up, we do a rolling restart on the pricing service, it would be pretty slow until we got a lot of the data cached. That's fine if you're doing your rolling restarts late at night, but if for some reason you had to do it during the day, not so good. And by slow, I mean that if the data wasn't in memory and my heap, and the NODB buffer didn't have it cached on the MySQL side, it could take up to 2 minutes to query. So obviously that's pretty bad. I couldn't afford to do that. So enter the Mongo. So I've been working with MongoDB for quite a while, and I was aware of the geospatial indexes in it, and so I thought, well, let's take a look. That probably will fit our use case, and fortunately for us, it worked out really well and kind of solved the problem for us. So MongoDB has a bunch of different types of geospatial indexes. And I'm not going to go into a lot of detail about MongoDB. There's a lot of information out there. There's a lot of information at this conference about it. So I'm mainly just focused on the parts of it that we used. So there were some standard 2D indexes in Mongo. When I started looking at it, for this, it was around 2.2 was the version of Mongo. And it was really just too slow for my use case. But there was another one called the GeoHaystack index. And it was a pretty interesting index. Turned out it was conceptually very, very similar to what we were doing in Java. It's basically taking a grid and just so like an XY rectilinear coordinate system and slapping it down on a whatever you're using, like say the Earth, your locations, or latitude, longitude, and then storing things inside of those grid cells. And so that actually worked pretty well. But just in the last couple of weeks, I've switched over to MongoDB 2.4, and it has a 2D sphere index. And it's a lot more flexible, and turns out that my testing shows it's actually even faster. So we'll be switching over to that in our September release. So just a quick aside on mappings and projections, and so the effects of using a non-spherical index. So when you look at something like Google Maps, you see what's called a Mercator projection typically, and it's a cylindrical projection. So if you just imagine the Earth and it's splatted out onto a cylinder, that's what it looks like on the map. And so there's definitely distortion that you get. And when you look at, say, the latitudes, as you go 10 degrees of latitude from the equator to a pole, it stays the same. So 690 miles, roughly, in between 10 degrees, for every 10 degrees. But with longitude, obviously the longitude is going to collapse down to 0 at the pole, and so the farther you go north, the more distortion you get. And so you have to be very careful about, if you're using the Haystack Index or any other kind of rectilinear index, not taking into account the spherical nature of the Earth, the farther you go north, the worse your results get, or the more inaccurate, and you have to account for that. So at the southern tip of the US, it's down to about 650 miles is 10 degrees of longitude. But even by the time you get to the northern part of the US, just a little bit above into Canada, well, above Montana and North Dakota, it's down to 240 miles. And so you can see there's quite a bit of distortion that's happening there. And also it makes these states look bigger. So, I mean, Canada's big, but it's not that big. As it sees on Google Maps, Montana, North Dakota, actually not that big. Texas, however, actually is that big. So the Haystack Index, so we used longitude, latitude for XY coordinate system. So you have to keep that in mind as well, because longitude is the X, and normally we always talk about latitude, longitude, but you have to reverse that. If you don't do that, you will get crazy, crazy results, and I can speak from experience. So then also, for us, our default search radius was 25 miles, and about halfway up through the US, kind of the midpoint of the US, that's about 0.5 degrees. So in the Haystack Index, you have to do all the radius and bucket size, all of that is in the same units as your coordinate system, which is a little bit funky. Our users don't typically say, they're not thinking, okay, I want to find a doctor who's within 0.4 degrees of longitude of my house. So you have to accommodate for that. And because of that distortion, if you don't, you end up with this elliptical search radius. And the ellipse gets really elliptical up in the northern part of the US. So you overcompensate for that, and that's what we did, and then go back and prune all the ones that fall out. They're too far away on latitude. And so this is just to show what it's like in MongoDB. So this is the JavaScript commands. The first one is to create that index, to create the GeoHaystack index. And when you do that, you can have, with a Haystack index, you can have one additional filter. And so in my case, the procedure mapping ID was the additional thing. So the thing that provided the most selectivity, of course, for me anyway, was the location and then the procedure mapping. And then the second is you just have to use this database command. And so in that command, I'm saying I've broken all of my pricing data into these natural buckets that are a simpler way of partitioning my system based on insurance companies and employers. And so I'm giving the search origin, the max distance in degrees, and then I can specify one value. And this is a little bit of a downside of the Haystack index. That second part of the index has to be a literal value, like a number or string. It can't be an array, which is too bad, because that would really have helped me. And so those are some of the drawbacks of it, but it's pretty fast. And then the third thing, a little bit of a bummer, is there's a bug in the Haystack index. If you try and search on the second part of your composite index and you don't have an index on it itself, a separate index, then you get an error. But if you're going to search on that, you probably want to have an index on that. So that worked for us pretty well up until now, but what started happening, again, your data changes. And so we started getting these buckets of data that, like one of them, we have 150 million prices. And a lot of the prices that are in there are out of network for the users, because there are a lot of provider networks and the user has access to a small number of those. So we're looking at a lot of data and then filtering based on the provider network on the app side. So I took a look at the 2D sphere index because it would let me have additional parts to the composite index. And it also supports Earth-like spherical geometries, which is great. So the default is, in fact, the Earth for the spherical geometry that supports. And then when you specify the location, I was still using XY pairs. It works out well, but you can use GeoJSON to specify the location of the document that you're inserting, and it indexes that. It also supports line, string, and polygon, so pretty good support for GeoJSON if you're already using that. It's pretty nice. And then the other thing with the Haystack index, the only thing you could do was essentially inclusion in a circle, and a flat circle. With the 2D sphere, there's besides inclusion, and there's inclusion in like, if inside of this polygon and inside of different shapes, can be quite nice, as well as intersection. Give me all the documents that intersect these two shapes in proximity to a point. Give me the top 100 documents that are close to this particular point. So much more flexible. And so for comparison, here's how you would actually use it. So the first command, again, this is the JavaScript of how you would do it. So like in the Mongo console, you can do this. So what I'm doing is inside of my pricing database, I'm saying I have a collection named Priceables1. There are a bunch of those in there. So on that collection, I'm telling it to make sure there's an index. So if it already exists, it just ignores this. Otherwise, it creates it. So create an index, make the first part of the index be a 2D sphere index on that loc key, and it's an array of longitude, latitude in my case. And then the second part of the index is the procedure mapping ID, which is a key on the document named PM. And then the third part of the index is the provider network. So then there's also a PN key that's on there. And it doesn't have to be in this order. If you found more selectivity by some other thing, and then the geospatial part it provided some additional selectivity but wasn't the most important, you could put it later. So 2D sphere is really a very flexible index. Then the second command here, this is just doing a search in it. So I'm telling MongoDB from the Mongo console to find all the documents where the loc key, and it was just what I named it again, is the key inside the document. And the geo within, so that's an operator in MongoDB, and it's basically specifying inclusion. And the shape that I want to find things that are included in is if you think of like a yarmulke, and somebody drops a yarmulke down a gigantic one, 25-mile radius yarmulke, drops it onto the earth, and so you get this spherical sort of cap sitting on the earth. That's the shape that I'm searching in. And so that's what I'm specifying here. I'm specifying the longitude and latitude of the center of that, and then the radius. But this time it's nice, it's in radians, because of course now we're in spherical coordinates, and so now I don't have to worry about distortion. And then finally I'm specifying that a particular procedure mapping, and then so there's another operator in MongoDB. It's very much like in SQL and in, so I'm just saying where the documents have this particular procedure mapping ID, and they have a provider network ID that's either of one of those. Return those back. So my results, so it's highly accurate, geospatial accurate. I didn't have to do any go through and do any pruning of the results that came back. And it was even faster than the Haystack index in almost all cases. And the main reason it was faster for me is that I really benefited from that third part of the composite index, and that made a big difference. So this is great. So now I have these geospatial indexes, and so I can search for prices based on location. But at this point, I was still using hard drives. And so the good thing is, so the MongoDB GeoIndex was twice as fast as Java on top of MySQL. But twice as fast just means it was 1 minute as opposed to 2 minutes. So that's pretty bad when the data was not cached. And so I spent a little quality time with IOStat and VMstat, and became pretty clear I'm suffering death by random read, just way too many random reads to find all the data. So I went out and got a $200 Samsung SSD, a little 256 gig SSD, stuck it in a Linux desktop, and now my typical query time went from a minute to well under 100 milliseconds for most queries, and even the big ones where I'm pulling back tens of thousands of documents, it was still taking only about 150 milliseconds. So it was really, really fast. So the MongoDB comes with this nice tool. It's just a generically useful tool. I mean, there are a ton of tools out there like Bonnie and stuff like that for measuring disk I/O performance. So MongoPerf is pretty great for that, and it has a mode that gives you a pretty good sense of how a particular device will work with MongoDB because of the way MongoDB uses memory map files. And so what I did, just to compare some things, so I've got enterprise-grade SSDs in my production and QA systems. And in QA, we're using VMware, I have VMs. So in the production system, I'm getting 74,000 IOPS. And so that's pretty great. With a hard drive, I was getting, with a RAID 0+1 array or 1+0 array, I was getting about 300 IOPS. So this is a huge performance boost. There is a drawback of going with virtualized I/O with VMware, so that kind of killed it down to about 30K IOPS. Still pretty great, but that definitely a noticeable cost. Now, this is I'm slamming the drive, you know, so it's not quite the normal mode of operation. But so you definitely want to keep that in mind of this huge win you get with an SSD. When you look at the percentage loss you get by running VMs on top of it, it's not insignificant, you know. So definitely consider that. And then just a consumer grade. An MLC 256 gig Samsung 830 that I had, I was getting 47,000 IOPS just sitting in my Linux desktop box. So that's pretty great. Run everything on that. Put your whole system on that, and you'll be happy. So so now I've got these geospatial indexes, so I can look up the data really fast. We can look it up based on these geospatial indexes, and it's fast on these SSDs. So now I want to get this data into my system. And how can I do this with having as little impact as possible on users? Because I want to be able to change this data just on the fly and have it be totally transparent to the user when I put in new pricing data. And so we do major price updates monthly, but I also wanted the flexibility of like whenever I wanted, like, oh, if we found an error in the data, or we just want to refresh the pricing data, I want to be able to do that during the day. And so the main thing to be kind of aware of in this that affects us is, for us anyway, for our use case, we're I/O bound. We're not CPU bound. These queries that MongoDB is doing, almost no impact. So I see like 0.1% CPU use across 6 cores. But the I/O can be pretty heavy, the load on the SSDs. So what I did is I set up 2 MongoDB replica sets. And I put multiple SSDs in the servers, and so I'm running multiple MongoD daemons on each of these servers. So this picture here kind of depicts what we did. And so the ellipses there represent the replica set, so prod pricing 1 and prod pricing 2. And so in MongoDB, a replica set, kind of the minimal replica set, has 3 members. And you have 2 members that have all the data. One of them, at any given time, one behaves as the primary and one behaves as the secondary. And then the third one is, if you're fine with just having the 2, is an arbiter. And so it doesn't store any data, has very little impact on the server it's running on. What it's doing is heart beating with the other instances and doing quorum voting. So if the primary were to go down, and that actually did happen for us recently, the arbiter and the secondary would vote. They would see, okay, we still have a quorum, and the secondary would be promoted to be the primary. The primary, let's say it was a network partition, then the primary would go, okay, I'm all by myself now. I will stop responding to requests. And so for me, what happened, so I've not had this problem with MongoDB, but I actually literally had the SSD die on me, and on the primary, of course. And MongoDB, very nicely, within milliseconds, failed over to the secondary. And so that was pretty awesome. So then I have the second replica set. And so these, in the first replica set, the instances, they're all listening on port 28001. And the other one, it's 28002, just what I chose, just to keep myself sane, of like 1s and 2s everywhere, so you can remember things. It's running on the same system. It's just its data directory is on a different SSD, so that I can load it kind of at will and have really no impact on the active replica set. And that turned out to work fantastic. So what I actually do is I load up all this data on our QA systems, and because the files are portable, of course, I just zip them up and use PGZ. It's super awesome. If you got a lot of cores, and then I transfer that data up to the SSD on the passive replica set. I put it on the primary and the secondary. I don't even use replication. I just literally like replace the data directories whole. And then I restart those MongoDB instances, and then it's ready to go. I have the new data, and that's actually pretty fast. Then Mongo has this other really nice thing, like if you use MySQL, or probably a lot of other databases, if you do like a select count star a lot of times on a transactional table, that will cause the database daemon to page it in. So with Mongo, and it's using memory map files, you get really great performance if your working set is in memory. And so there's a touch command, and it very, very efficiently reads 1 byte from every page. And so that will page. For a particular collection, like in this case, the Price Bills 1 collection, it will page in all the indexes, so all my geospatial index and all the parts of it. And then if I specify data true, it will then page in actually all the data as well. And so as much memory as you've got, you definitely want to pull it into memory. And then on my pricing service, I just have an operation on it where I can hit the pricing service instances kind of across all of our app servers and have it flip. So I just tell it, essentially I'm just telling it, connect to this other replica set. And when you do that, you want to tell it, when you tell it to connect to the other replica set, you want to tell it all the servers that make up the replica set. If you just tell it one, it'll find it, and it will use that part of the replica set to find all the other members. But if your pricing service restarted and it has to look up that information, and that guy happens to be down, then it won't find it. So definitely important to do it that way. So the drawbacks of doing this, so there's a little bit of extra cost, but it's only the extra SSDs. I didn't have to have separate servers. And we're running on managed servers at Rackspace, and cost is a big factor here. These are pretty big machines. So I'm running, they're 128 gig machines with 6 cores and obviously these SSDs. So I wanted to minimize the number of machines that I had. And I only needed one replica set to have its data in memory at a time. So, if I had a passive replica set on other servers, they would just be sitting there totally unused, the actual server itself. So that's all read-only data. So this is great. So this works really well if you have a lot of read-only data. So we started adding caching though as well, and so we're caching data from remote pricing lookups into these MongoDB instances. So of course I'm going to lose that when I flip. And MongoDB does have this really nice feature called TTL collections. It's kind of like, we also have Memcache in our architecture, and so very similar sort of functionality, evicts it after a certain time that you set for the item, but it was just nice to keep everything in Mongo. But we do this flipping late at night, and it's only a 3-hour cache, and so there's really not that much cost to basically flush the cache when I flip over. So the results that we ended up getting is with a cold cache, as opposed to 2 minutes or even 1 minute, now it's totally acceptable. It's like maybe 100 to 200 milliseconds, kind of worst case if the cache isn't even warm, just hitting things off the SSD. If I have a warm cache, performance is really awesome. It gets down into tens of milliseconds to look up all this data. And then the pricing service startup, as opposed to taking over an hour to do a rolling restart on my app servers, now it's just a couple of seconds per instance. Because now the performance is so good, I don't do any caching in the service layer. I just don't have to do it. Mongo does it all for me. And now I can do these major rate updates, and there's no production impact. So actually, if I did want to do it during the day, that would be totally fine. I could flip over to another replica set. I can load the passive replica set during the day as well and not impact production, and which lets me do these minor rate updates, which before we could never do anything like that. So then in summary, the GeoHaystack index, if you're retrieving a lot of documents in a, I say a constrained search area, but we were searching out to 100 miles. And performance was still pretty good. And you've got very simple geospatial searches, because again, it only lets you show me all the things that are inside of this circle in a flat 2D coordinate system. And if you only have a single secondary filter. So if that's your case, which ours initially was, that was exactly our case, then it works really well, and it's pretty easy to use. There's not a ton of documentation, but it's not that hard to figure out. If, however, you have a more complex type of searches that you need to do, or you need to do more complex indexing, like that secondary part of the composite index doesn't provide enough selectivity, then you definitely want to look at the 2D sphere. In general, I would say look at the 2D sphere, and probably at this point not really bother with a haystack index at all. SSDs, if you've got a lot of random reads, it's just a massive, massive win. The value is enormous there, and you can get huge performance huge performance boost at a fairly low cost. And it definitely reduces your need for complex indexes. And then replica set flipping, it's going to work great if you do need to do these fairly instantaneous swaps of large amounts of data, and your data, it's primarily read-only, maybe if you have a cache that you don't mind losing. And so it's a fantastic trade-off of cost for operational flexibility. So, all right, so any questions? Yes? Yeah, so the question is about, so that's a good question about where the reads and writes go. So the writes always go to the primary, and they get, so when I'm writing to the cache, it gets replicated to the secondary. when I do the reads, there's with MongoDB, with the drivers, there are read concerns and write concerns. And so, or write concerns are kind of the main thing. But with the read concerns, you can do things like you can say, I'm fine with reading from slaves, or I want to read from the slaves, from the secondaries. There's also another one set that's, what I want to do is read from the nearest. And so that's really good if some of the members of your replica set are remote, or they're even in a different rack. And so it will prefer, and it keeps track of ping times, and so it will use the instances that are closest to it. And so that's what I use, because since the data is not changing very much, and it's between the big bulk data and then the cache, if I don't find it in the cache, even though it's really there on the master, it's not that big of a deal, then I'm fine with that. And so if the master got really heavily loaded, the primary got really heavily loaded, then all the reads would start going to the secondary, and I would get some load balancing there. And so then if eventually I got to the point where I really had a lot of load, I could just start adding more secondaries to this, and more of the reads would just automatically get offloaded to the secondaries. So other questions? Yes?
Can 2D Sphere be used for polygon searches? So I want to be able to search a rectangle instead of a sphere, or anything like that. So I want to find everything within this area.
Yeah. So the question is whether you could use polygons for searching versus a sphere, and absolutely. So when you do the search, that geo within, so you're saying, I want to find things included in this shape. And in my case, the second operator that I specified was center sphere, and so that was the circle kind of projected. But I could specify a polygon at that point. So you can specify the points, the GeoJSON points that make up a polygon, and it will return just the documents that are included in that polygonal shape. Yep. Okay, anything else? All right, thank you very much.